Assalamualaikum warahmatullahi wabarakatuh and hello everyone. We are from Group 3, Section 2 and this is our video presentation for Chemical Reaction Engineering Project and the title for this project is Synthesis of Isopropyl Benzene. Our lecturer is Professor Madia, IR Dr. Nozita Ngadi. My team consists of me, Muhammad Herman bin Ahmad, Muhammad Aliff Danish, Nur Murshidah and Nur Sabrina.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Sabrina Abd Rashid and I will start with literature review, and for the first part is the process review. Isopropyl benzene plays a crucial role in the production of phenol and acetone. Traditional catalysts like aluminum chloride and phosphoric acid used in the alkylation of benzene and propylene pose drawbacks such as lower quality, reduced efficiency and environmental concern. However, zeolite have emerged as superior alternative due to their open structure and strong acidity. The shift to zeolite catalysts enhance performance and environmental advantages. In the liquid phase process using beta zeolite, chumine selectivity ranges from 70% to 90%, achieving yields close to 100% with excellent purity in the production of alkyl aromatics like chumine. Next, isopropyl benzene production involves a fixed bed reactor with multiple stages where benzene and propylene are mixed. The reaction in the liquid phase requires pressurization 25 to 35 bar and heating 150 degrees Celsius to 200 degrees Celsius. A minimum molar ratio of 4 to 1 benzene to propylene is crucial to enhance chumine selectivity and manage heat from exothermic reaction. A low benzene to propylene ratio can lead to catalyst deactivation, incomplete propylene conversion, or the presence of impurity and propyl benzene due to a very high reaction temperature. For background of chemical product, chumine or isopropyl benzene is a volatile liquid with a sharp smell. It is part of the alkyl aromatic hydrocarbon family found in crude oil and gasoline. While it doesn't mix with water, it dissolves in alcohol and organic solvents. Chumine vapor exposure can be harmful, causing issues like central nervous system, depression, and irritation. For a quick overview, review to Table 1 for the chemical and physical properties of pure chumine.
The consecutive mechanism for benzene alkylation with propylene consists of two primary stages, which are protonation step and alkylation step. The reaction pathway commences with propylene being adsorbed onto the acidic side of H-beta. This adsorption positions propylene at the proton side, causing distinct distance to emerge between the proton and the two carbon atoms in propylene. In step A2, a chemisorption transition state is formed involving the protonation of propylene at the C1 atom to produce isopropoxide intermediates. In step A3, it undergoes conversion into an isopropyl intermediate. The energy released during the formation of isopropoxide in relation to the absorption complex is exothermic, signifying that the isopropoxide configuration is a more stable intermediate in chemical adsorption. Then, it combines with nearby benzene to produce physisorped benzene in step A4. Moving to the alkylation step in A5, the alkylation transition state involves the establishment of C2 and C1 bond between benzene and propylene. During step A6, the chumine absorbed on the zeolite undergoes the formation with an endothermic energy in contrast to the physisorped benzene. Ultimately, the reaction concludes with the desorption of chumine from the H-beta zeolite in step A7. Next is the desorption of chumine from the zeolite. The co-adsorption is similar to the propylene absorption observed in step B1 of the consecutive mechanism, confirming the weak adsorption of benzene on the zeolite. The propylene absorption on the proton side of the zeolite closely resembles that in the consecutive mechanism pathway. Step B2 involves the concurrent processes of protonation and alkylation through a transitional state. This transition state entails the cleavage of the bond between the active center HA and the zeolitic oxygen O1, leading to the transfer of the HA proton for the protonation of propylene through the C1 atom. The product, which is chumine, takes shape through the back donation of the proton to the zeolite framework in step B3, with the reaction energy relative to the co-adsorption complex being exothermic. Finally, the alkylation reaction concludes with the desorption of chumine from H-beta zeolite.
Our main reaction is reaction between propylene and benzene to produce isopropyl benzene. In this case, we indicate propylene as A, benzene as B, isopropyl benzene as C, and diisopropyl benzene as D. The reference rate law for the first equation is negative R1A equals to K1 CA1 CB1. And for the side reaction, the reaction is between the isopropyl benzene and propylene to produce diisopropyl benzene. And the reference rate law equation is negative R2C equals to K2 CC2 CA2. There are two typical reactors for this reaction. which are CSCR and PBR. CSCR is suitable for high reaction rate and also able to maintain the concentration of the reactant. However, it is not recommended for a reaction that produces byproduct. And for PBR, it gives a slow reaction with a high selectivity. We can control the temperature and also it is suitable for reaction involving catalyst. So since this reaction produce a byproduct which is diisopropyl benzene, it is good to choose PBR because it can give a high selectivity to our desired product which is isopropyl benzene.
Next, I will explain about the reaction kinetic. Reaction kinetic is a study of the rate at which chemical reactors occur and factor that influence this rate. It involves with the reactant concentration and the reaction rate. This is the summary table that show the difference between three journals that relate to the reaction kinetic. These journals show that the main and the side reaction are the same. However, the rate law for main and the side reaction for each journal is not the same, as it influenced by various factors including the value of alpha and beta that we get experimentally. These journals also show the range of temperature and pressure used for each reaction to occur.
So for the reactor system for this project, we choose the fixed bed reactor (PBR), and the reason why we choose it because it has a lower capital and operation cost and requires a small volume for reaction compared to a fluidized bed reactor. And in addition, the causing is because less of catalyst loss, and it also easier to operate and have a low maintenance cost. This is the design of our reactor for PBR. So for this reactor, the reactant will be insert from the top and the product will go out from the bottom, and at the side we have a heat in and heat out, and also the catalyst is inside the PBR reactor. And for the parameter, the length of the reactor is 2 meter and the diameter is 0.664 meter.
Next, I will continue with our MATLAB program where we need to calculate the selectivity for the main product and yield of all product produced in the process for isothermal and isobaric condition. For MATLAB program, user need to give an input for pressure, temperature, and mole fraction for the limiting reactant, which is mole fraction for propylene, as all of these variables influence most of the equation used in this calculation. In this calculation, we use 3000 kPa, 0.2 mole fraction of propylene, and 433.15 Kelvin. After we insert all of the three variables, we get K1, K2, B node, B and C and node, where K1, C and node and B node will be used to calculate weight of catalyst, and from this MATLAB calculation, we get 2.3816 kg of catalyst to produce isopropyl benzene, where the process will run 3 hours per day. C and node also will be used to find the final concentration for each substance for the first reaction and the second reaction. C and node, the final concentration as well as K1 and K2 was used to calculate the net rate law, where it will be used to find the selectivity and yield. For selectivity of desired product, which is isopropyl benzene, we got 143.8903 and the yield is 14389.0259. Meanwhile, yield for the undesired product, diisopropyl benzene, was 0.0069. A high selectivity and yield for the desired product is generally better in chemical process, as it indicates efficiency and cost effectiveness. Meanwhile, a low yield for undesired product is preferred to minimize waste and maximize the utilization of resources, contributing to a more economically viable and environmentally friendly process.
In conclusion, the success of this project underscores the critical importance of selecting an appropriate reactor with the right size, diameter, and length. The choice of a packed bed reactor PBR proved advantageous, particularly to its involvement with the catalyst. Understanding the entire reaction, including main and the side reaction, was crucial for the synthesis and managing multiple reactions. Moreover, the project provides a valuable opportunity for students to develop MATLAB coding simulation, enabling users to input different variables and enhance the understanding of reactor dynamics.